All right. In this particular lecture, I want to devote some time to the process, or the last formed element of the blood, known as platelets, and talking about the role that they play in blood. Now, just remember that the formed elements are the cellular components of blood, while plasma is the water and all the non-living organic and inorganic materials of blood that are dissolved in it. All right, and the three types of cells that you find in blood are going to be erythrocytes, or red blood cells, which are your transport cells for primarily for gases, like oxygen and carbon dioxide. Then we've got leukocytes, white blood cells, which are essentially your immune system. But bear in mind that leukocytes that are in the circulation more than likely are on their way to another tissue, in order to be stored or to get into that tissue to attack a foreign invader or whatnot. And the last type of cell is a platelet, otherwise known as a thrombocyte. Okay, otherwise known as a thrombocyte. Okay. And the main function of platelets is a process that we're going to be talking about towards the end of this discussion. That's what the bulk of this discussion is going to revolve around. It's a process called hemostasis, or the controlling of bleeding. All right. So again, platelets are known as thrombocytes. Now, platelets are, in a true sense, not technically a cell. They're fragments of cells. Okay, they're very small, granular fragments. Okay, so one, you have to bear in mind that they're about 2 micrometers in diameter, very, very small, and they contain granules. Okay, and it's very important because we're going to talk about some of the material that is released from these granules in a little bit. Okay, because these secretions that are released from the granules that are within the platelet are highly important for the formation of a clot. Okay, the attraction of other platelets and activating clotting factors and so on. Okay, so those secretions are highly important, and platelets also have actin and myosin within them, so they've actually got contractile proteins within them. All right, and that's a very important characteristic or feature to have, because let's say, for example, we damage a vessel, and then all these platelets start to plug the hole of the vessel. What they tend to do is they contract and then pull the damaged ends of the vessel, together to close off the hole and further control the blood loss, the situation there. Okay, and normal platelet counts tend to run between about 130,000 to 400,000 platelets per microliter, typically if you go above if you go greater than this value, then a person may be susceptible to forming too many clots and may develop what's called a thrombosis, and those clots may get stuck in areas of the body where we don't want them to get stuck, the microcirculation, or they may get stuck in a piece of plaque that is in a vessel somewhere, and that can cause an infarction and cause damage and possibly kill. Remember, the word infarction means when you cut off the flow of blood to a tissue, that tissue is deprived of oxygen, and then the tissue starts to die and will die if the blood flow is not restored. Okay, and then if your platelet count gets below 130,000 platelets per microliter of blood, then we're going to say you have a hard time forming clots. Okay, and the problem with this then is if you have a difficult time forming the clot for whatever the reason may be, then when you get it cut, you bleed and you bleed and you bleed and you lose blood. Okay, so hemostasis is not going to be working very well if you don't have enough platelets. Okay, so essentially the primary function of platelets are, as I mentioned earlier, hemostasis, or the formation of a clot. And that's what these granules are for. They secrete these factors for the formation of a clot that aid in vessel repair, and they also play a role in dissolving the clot as well, because once the vessel is repaired, we don't need the clot there anymore. Okay, but that's what I want you to think about platelets is doing, as they're involved in clot formation. And then when you take a look at platelets here, when you look under the microscope, they're going to be relatively easy to spot, because platelets, another thing about platelets you have to remember is platelets are very sticky. Okay, platelets are very, very sticky, all right? So platelets are going to circulate around the blood in clumps, all right? So you're going to see some clumps around, and then you might see a clump over here, might see a clump over there, all right? But you typically don't see individual platelets. You see chunks of platelets are too small to see individually, all right? But when they chunk together and then circulate around, then you can see them. And then obviously these would be the rest of these cells you would see be erythrocytes, and then all this space around here would be plasma around the cells. Okay. So platelets again are pretty easy to spot. Just look for the little clumps, the non-cellular clumps. Okay, and then platelets come from. Now, as I mentioned before, platelets in a true sense are not cells. What they are is they're fragments of cells. Okay, so basically, like all other blood cells, the chemical message that stimulates the formation of these are, colony forming units, and the right messages here, the right colony forming units, could potentially stimulate these hemopoietic stem cells, or I'm sorry, these pluripotent hemopoietic stem cells, these PHSCs, to form into what's called a cell called a megakaryocyte. Okay, and basically these are derived from myelocytes, basically a class of stem cells that winds up forming into the granulocytes, or the types of white blood cells. Well, megakaryocytes also come from this particular class of stem cells. So essentially, when the right CFUs are exposed to this particular stem cell, they start to divide, and then what they do, instead of forming into neutrophils, eosinophils, or basophils, or monocytes, what they do is they differentiate into a cell called a megakaryocyte. Okay, megakaryocyte, mega for big. These are big cells. Okay, megakaryocytes are about 100 micrometers in diameter. Okay, very large cells. Now, megakaryocytes, they remain in the bone marrow. The red marrow. Remember, we said that blood cells are produced in red bone marrow. Okay, so these cells remain in the red bone marrow, all right? And what they do, once we develop mature megakaryocytes, is they create these little invaginations of their plasma membrane, and then they break off. Okay, and then these chunks that break off, take some of the, the cytoskeletal proteins and other enzymes with it, and then those are platelets. Okay, so megakaryocytes just sit in the bone marrow and slough off pieces of itself and its skeleton and other material that's within it, and then those pieces, those granular pieces, are platelets. Okay, and remember, those pieces are also sticky. These platelets are going to eventually kind of start to clump together and then circulate around the body in chunks, as I just mentioned. Okay, so that's essentially where platelets come from. They're just fragments of large cells called megakaryocytes. All right. Now, and as I mentioned before, the major function of platelets is hemostasis. Hemostasis is a very rapid reaction to trauma to blood vessels. All right. And how quickly this process takes place ultimately depends on usually the extent of the damage. Usually minor damage elicits a little bit of a slower response. It could take up to maybe 1 to 5 or 6 minutes to really start to get the bleeding under control. Or if it's severe trauma to a vessel and tissue, it could be anywhere up to 15 seconds to really start seeing some progress. And you'll see why in a little bit. All right. Now, when basically, remember, one thing you have to bear in mind about this is the circulatory system is a closed system. Okay, I know I've said this before, but I need to bring this point up again. It's a closed system, meaning that we should not be losing blood. Okay, even though fluids leak out of capillaries into tissue spaces, those fluids also, the plasma essentially, that water leaks back in. Okay, I should say it's more drawn back in. Okay, it's forced out of the capillaries into the tissue spaces, where we then deliver gases and nutrients. And then when it is pulled back into the bloodstream, that's where you get, carbon dioxide and wastes are pulled back in. So even though we're pushing water out of the cardiovascular system into the tissue spaces, 100% of that water is going to be reabsorbed back into the bloodstream to maintain constant blood volume and water balance in the body. All right. And then there are problems that can come along with that, but that's not a topic for right now. Okay. So this is a closed system, all right? And you know that the cardiovascular system, essentially it's a system of a pump, i.e. the heart, and basically major vessels. Oops, made the aorta go the wrong way. Okay. Major vessels that transport fluid. Okay, and that fluid is blood. All right. So these vessels would be like pipes. All right. And just like a pipe in your house, if you break, if a hole gets broken in your pipe for whatever reason, or there's a crack in your pipe, okay, you have to stop the leaking. Okay, you have to stop the leaking. And if you don't stop the leaking, this water's gonna keep pouring out. And what if you run out of water? Well, then you can't use your sink, or you can't use anything else that requires water flowing through that pipe. Okay, same thing with the body. If we break a vessel open and it just bleeds and bleeds and bleeds, and we lose that blood, bleeding blood that's lost out of blood vessels, that's blood that's not being circulated around the body and supplying our tissues with oxygen, or gathering waste products and transporting them to the areas of the body for them to be eliminated. All right, so we need that blood to remain in the cardiovascular system, so we can quickly and effectively transport material around. But we do break vessels open. I mean, we cut ourselves all the time. All right, it happens. Now, there are three major stages of the hemostasis process, and I have them listed in order of how they, or when they happen. And then we're going to talk about how they work in a second here. So the first event in hemostasis is vascular spasm, basically the constriction of the vessel that is damaged. Okay. Then next we've got platelet plug formation, which essentially would be platelets aggregating in the area where the damage is and plugging the hole. And then coagulation, this is when we form the real clot. So this platelet plug is not a clot. Okay, it's not a clot. But when we take this little plug of platelets and then we combine it with a protein called fibrin that wraps around that plug and makes those platelets stick together a lot more securely, now we've got a clot. Okay, that is a clot itself. All right, and those events occur in order. And bear in mind that this is a positive feedback cycle. It just gets more amplified until the bleeding stops. Okay. Now, before I get into that, before I get into this entire process, you have to understand, this may have popped into your head already, but if it hasn't, why don't platelets already stick to the walls of blood vessels? Okay, why don't platelets just stick to vessels? Because I mentioned earlier that they're sticky little clumps of cell fragments that are pumped around the body. So why aren't they always being glued up against the vessels? And that has to do with the structure of a blood vessel. Okay, so if we were to look at a vessel, all right, blood vessels have histologically have three tissue layers, that are called tunics. Okay, tunics, and there's a tunica externa, a tunica media, and a tunica interna, otherwise known as the intima. Get used to seeing that word, intima. All right. So the tunica externa is just some, loose connective tissue, some collagen fibers that are just, wrapped around the vessel, keeping the vessel organized. It's where you find the vasa vasorum in many vessels. Those are small vessels that supply the vessel itself with blood. And then you've got the middle layer of the blood vessel, the tunica media, remember media middle, which is smooth muscle, okay? And depending on what type of blood vessel is we're talking about, there could be a heavy wall of smooth muscle if it's an artery, or it could be a very thin wall of muscle if it's a vein. All right. And if it is an artery, a big artery especially, there's a good chance there's also going to be a lot of elastic fibers in there. All right. And then the deepest layer of a vessel is the intima, or the tunica interna. And then found lining the intima are cells called endothelial cells, which are highly important to a lot of properties of this blood vessel. Endothelial cells are basically simple squamous cells that are found encircling the entire inner lining of the vessel. So the endothelial cells are in contact with the lumen of the vessel. Remember, the word lumen means the hollow part of an organ. Okay, blood vessels, your GI tract, your urethra, whatever. Okay, although whatever organ is you want to think of that's hollow. Okay, the actual hollow space inside that organ is called the lumen. Okay, so the endothelial cells are not only in contact with the lumen, they're in direct contact with blood. Okay, so you should be thinking that, well, why aren't platelets, excuse me, why aren't platelets sticking to these endothelial cells? And it has to do with the endothelial cells themselves. They produce anticoagulating or anticoagulant-like chemicals that prevent them from actually sticking to the walls of the vessel to prevent undesirable clotting. Okay, and lots of antithrombolytic substances that would break up a clot if they started coming in contact with it. Prostacyclins, which prevent the platelets from sticking to the walls. Okay, so as long as the blood vessel is intact, all right, as long as this vessel is intact, is not broken open or damaged, what was I going to say? As long as it's not broken open or damaged, the platelets are unable to adhere to the walls of a vessel, as long as the vessel is healthy. All right, but we're going to talk about what happens when we break and damage a vessel. All right. And there are three parts, like I said, the three stages of vascular spasm, formation of the platelet plug, and coagulation. All right. So let's say we damage that vessel. That vessel broke open. All right. So the first stage that you're going to see. So let's say we've got the vessel here. All right. But now all of a sudden, and then let's say this is the inner part, the hollow inner part of the vessel. Now, what's going to happen? Okay, so we damage this here. So what's going to happen then is the vessel itself is going to constrict, especially in the area where the damage took place. Okay. That's going to be a vasospasm. Vascular spasm. Now, what's going to cause that? There are pretty much three major causes of vascular spasm. Okay, one of them is just a direct injury to the vessel itself. A direct injury is going to cause the muscle tissue of this vessel to constrict. So it's going to go from looking like this to looking like this. Okay, so in the area where the damage took place, it's going to constrict. All right, and part of that's going to be caused by the direct injury. Part of that's going to be caused by, when the cells, some of the cells that are damaged and broken open in the area are going to release chemicals that are going to stimulate the muscle tissue to contract. Platelets also do this. Okay, platelets, remember we said platelets are granular cells. They're going to dump out some chemical messages that are going to stimulate that smooth muscle to constrict. All right. And then also, this is also going to be maintained and regulated neurologically. This is going to activate nociceptors, and which will, obviously, communicate with the brain and say, remember, nociceptors are pain receptors, and then will carry out an appropriate reflex to maintain the vascular tone of the smooth muscle of this vessel, so the vessel can remain constricted. Okay. Now, why is this important? All right, why is this important? It's important for a couple of reasons. One, think about it this way. If you have a hole right here and you constrict this vessel, okay, now as blood is going to be flowing through here, this is going to increase resistance to flow. This is going to be a reflexive increase of peripheral resistance. All right. So basically, as this vessel constricts, it's going to be harder to get blood through here. The harder it is to get blood through here, the harder it is to lose it. Okay. Also, this is going to be important because when this vessel becomes damaged, now those endothelial cells are damaged. Remember, we said the endothelial cells are what produce those various chemicals and anticoagulants that prevent platelets from sticking to the walls of a vessel. Now, with the endothelial cells damaged and missing, what you're going to see is exposed collagen. Okay, you're going to see exposed collagen fibers, and those collagen fibers are going to project into the lumen of that vessel. All right, now there's something for platelets to stick to. All right, and think about it. If this vessel constricts, you're going to dangle those collagen fibers deeper into the lumen of the vessel and increase the chances of platelets actually, clumping up against them and sticking to them. Okay, so that's the first part of hemostasis, the vascular spasm. Next is what's called the platelet plug formation. Platelet plug formation. All right, so basically this is what I was just talking about a second ago. This is when, okay, so we've got these exposed collagen fibers. This is when platelets are going to actually stick up against these exposed collagen fibers. Okay, and then when they stick to those fibers, they're going to degranulate. All right, they're going to degranulate, and then they're going to release a kind of a bath of chemicals into the bloodstream, into that area where where the damage has taken place. And some of those chemicals that are going to be released, one of them is going to be serotonin. Okay, so that name probably sounds familiar if you studied the brain, because serotonin is a neurotransmitter in the brain. Okay, that deals with moods and so on, and other functions as well. But most people talk about serotonin in terms of depression and moods. All right. Now, serotonin is going to promote and allow chemically allow the maintenance of that vascular spasm. Okay, so working with the nervous system, the serotonin is going to allow this blood vessel to remain constricted. All right. Now, another chemical that's going to be released as the platelets degranulate is going to be ADP. Okay, ADP, what it does is it attracts other platelets to the area. Okay, it causes them to be attracted to this area and degranulate. This is where the positive feedback mechanism comes in. All right, because as long as these collagen fibers are exposed and there's a hole in this vessel, more and more platelets are going to stick to these. And as platelets stick to these, they're going to release more of these chemicals into the bloodstream. And then more platelets are going to get attracted to this area. And then more and more chemicals are going to be released. See how this is an amplifying process here? Okay, so as long as there's blood leaking out of here and there are no endothelial cells present because that vessel wall is damaged, then they're just going to sit there and degranulate and attract more platelets to the area. And you can see why we call this the platelet plug, because that's what these platelets are doing. As they're sticking to those exposed collagen fibers, they're plugging the wall. Okay, they're plugging the wall. And then another chemical that is released, or by these platelets, it should be thromboxane A2. Sorry, that didn't transfer over here like it should have. Okay, thromboxane A2. All right, thromboxane A2, like serotonin, allows the maintenance of the vascular spasm and also makes platelets a lot more sticky. All right, it makes them stick together a little more tightly. Okay. So that's the second part of hemostasis, is getting these platelets to the area and plugging the hole. And that's what those chemical messages do. So again, serotonin maintains the vascular spasm. ADP attracts more platelets and makes it easier for them to degranulate. Thromboxane A2 also maintains vascular spasm and makes platelets more sticky. So all three of these chemicals are being released at the same time. Okay. Now, there is a third step in this, because this sounds like a sweet idea. Okay, well, you get these platelets all stuck together, they plug the hole, great. They're not that good at staying stuck together for very long. They're sticky, but they're not that sticky. Okay, and if we were unable to actually secure this plug, those platelets would eventually break up, fall apart, and then this process would be meaningless. All right, that's why the important third step is coagulation. All right, coagulation. And coagulation is when we actually form a clot. Okay, so we still haven't formed a clot yet. Okay, what a clot is, it's the platelet plug. So essentially platelets plus the protein fibrin. Okay, when you throw that protein in the mix, now you have a clot. Okay, and remember, fibrin is fibrin comes from the plasma protein fibrinogen. Okay, it's converted from fibrinogen into fibrin. Now, coagulation is basically created by a pretty large array of chemicals that are found normally in the bloodstream that are inactive. Okay, and those chemicals that are in the bloodstream are called clotting factors. Most of the clotting factors are just inactive enzymes waiting to be activated. All right, and once they're activated, they basically, like any other biochemical reaction, move step by step by step, reaction after reaction. This is, that's why they say this is like a waterfall or a cascade of chemical reactions. So once you initiate it, it's going to just go right down the line. Okay, and basically all these steps you're going to see here are all about one thing: getting fibrinogen and converting it into fibrin. All right, and there are essentially three separate pathways in which all these processes occur. All right, there essentially is the intrinsic and extrinsic pathways. There's the conversion process of prothrombin into thrombin, so the conversion of one protein into another enzymatic form, and then the conversion of fibrinogen to fibrin. Okay, and thrombin is the enzyme that does this. Okay, so now let's talk about this and how this works, the formation of a clot. All right, so first we'll talk about let's talk about the extrinsic pathway first and some of these clotting factors involved. Now, when we're talking about the extrinsic pathway, what essentially is going to happen, we're going to have the tissue damage. Okay, and then the tissues, now the tissues are going to release these chemicals into the bloodstream called tissue factor. All right, so for example, I'm just going to abbreviate factor. Okay, so for example, if you have a nail go through your arm for whatever reason, okay, if you have a nail go through your arm, and obviously that's going to cause bleeding. Okay, the tissues, your skin and so on, the cells from the tissues that are adjacent to that blood vessel are just going to dump out these tissue factors into the bloodstream. And bear in mind, the more that these tissue factors are available, the more amplified this process becomes. That's why I mentioned earlier, the more extensive the tissue damage, the stronger this response is. You know, the stronger the hemostasis response is. You know, we more quickly respond because there's more clotting factors and chemicals available to essentially form a clot. Okay, and what tissue factor is going to do is it's going to start activating certain clotting factors. The first one is going to be clotting factor 7. Okay, and then what it's going to do is it's going to activate, then once clotting factor 7 is activated, you would write it as, you know, Roman numeral 7 and then A for activated. Okay, and then that essentially is going to activate clotting factor 10. Okay, clotting factor 10. Also, what is mixed in here with this is calcium. Is the board going nuts on me? Oh, gosh dang it. 1 second, folks. My board is going crazy on me here. Okay, so it's going to be, there we go. Oh, what in the heck? All right, there we go. Sorry about that, folks. All right, so basically when you mix clotting factor 7 with calcium, that essentially is going to activate clotting factor 10. Okay, and then we would label that as XA. All right. Then, once clotting factor 10 is activated, all right, that's going to activate an enzyme called prothrombin activator. Okay, but in order for this to properly become activated, there also has to be calcium in the mix. All right, some of these tissue factors, you know, are going to have to be involved in this as well. Excuse me. All right, now what's going to happen is once this prothrombin activator is activated, then you are going to activate the enzyme prothrombin, which will in turn, you know, activate thrombin. Okay, and as I just mentioned earlier, thrombin is the enzyme that converts fibrinogen to fibrin. Okay, fibrinogen to fibrin. Okay, what's also important in this process of converting prothrombin into thrombin are platelets, more specifically the phospholipids within the platelets, okay? So, phospholipids, can't spell today. Okay. All right, so bear in mind the platelets are going to be in this area, and as these platelets are sticking together and plugging this hole, they may be breaking apart, and then lipids are going to be, you know, phospholipids from the membranes and the platelets themselves are either going to leak out or be secreted out of them because they have Golgi in them. As a result, when you combine those with prothrombin, then you get thrombin. Okay, so basically this is called the extrinsic pathway. All right, this is called the extrinsic pathway because this pathway of creating thrombin was initiated by chemicals that were secreted from tissues outside the vessel that were adjacent to the vessels. All right. So all we did was, so you see the kind of the waterfall or the cascade effect. All right, now, as long as thrombin is active, okay, thrombin can act like a rate-limiting enzyme, essentially, to basically keep this process sped up. So basically, thrombin, what it does is it interacts with a clotting factor 5, all right, and and then clotting factor 5 essentially can speed this up. So basically, if we crank out thrombin at a faster rate, or as long as thrombin is around, and this clotting factor 5 is activated, we can produce clots more quickly. Okay, so that's all you're looking at here, is you're just looking at a step by step by step. Okay, we turn on one enzyme, and then we use that to convert, one enzyme into another. Then we convert another enzyme into another, and then into another, and then into another. Okay, so normally, as I just mentioned, these clotting factors are inactive in the bloodstream. So you saw what activated them here in this extrinsic pathway, the leaking out of these tissue factors from the damaged tissue. All right, so that's one way that we get fibrin, so we can convert fibrinogen into, how we get thrombin, so we can convert fibrinogen into fibrin. That's the extrinsic pathway. Now, the other pathway, don't want to erase all this. Insert blank page. Let's do this. All right, there we go. The other pathway to do this is called the intrinsic pathway. Okay, so now the intrinsic pathway occurs because of the contact with the damaged blood vessel itself. All right, so basically, so let's say we've got a damaged vessel here. Okay, that's a damaged vessel. So then what's going to happen is there's going to be a clotting factor 12, that's going to come in contact with the collagen of the damaged vessel. Okay, and once this comes in contact with the collagen fibers of this damaged vessel, that is going to activate clotting factor 12. So intrinsic, we're actually coming in contact with the vessel itself. All right, and then now we're just going to start this waterfall of effects. So first we'll have the activated clotting factor 12. So we would write that as 12A. All right, which will then in turn activate clotting factor number 11. Now in order to do this, there has to be some other proteins involved that allow this to happen. Okay, called HMW, high molecular weight kininogen, and all right, so high molecular weight kininogen. And then basically this, this allows us to, and then this is accelerated by other chemicals as well. And then once what was I going to say? Once clotting factor 11 is activated, all right, now we're gonna activate clotting factor number 9. I know it sounds kind of goofy going in this numerical order, but that's just how these chemicals work. All right, now in order to do this as well, there needs to be calcium available. Okay, and then what happens here is once clotting factor 9 is activated, we now activate clotting factor number 8. So 8A, which will activate clotting factor number 10. Okay, clotting factor number 10 then will basically activate prothrombin activator, which you know already is going to activate thrombin, which will in turn convert fibrinogen to fibrin. Okay. Now, thrombin that is already being produced can also enhance the step with clotting factor number 8. Okay. Also, once clotting factor 10 is activated, thrombin can also, enhance this process as well through the activation of clotting factor number 5. Now, one thing I did not mention yet is that in order to activate this prothrombin activator, calcium needs to be available, And just like the other pathway we talked about, the extrinsic pathway, platelets, there has to be lipids available as well to activate prothrombin activator. Okay. So basically, all you're seeing here, I know that may seem confusing. You know, you're going from, you know, clotting factor to clotting factor to clotting factor to clotting factor. But again, what you're realistically looking at are just step by step by step by step activations of enzymes that are going through these pathways, and the end goal is to get fibrin going. All right, so we can form the clot. Now, this process is a lot more slow. Okay, it's a lot more slow. This does not turn out, you know, fibrin as quickly as the extrinsic pathway. Okay, and like I said, the extrinsic pathway, how quickly that's going to turn out fibrin is going to really depend on the extent of the tissue damage. Okay, so the more damage the tissue, the more tissue activators that it's going to, or tissue factors that it's going to release, the faster and more rapid the rate, the more intense the rate is going to be. Okay, and then in the end, once we form fibrinogen, all right, once we form fibrinogen, then let's go to another page here, and let's doodle our vessel here real quick. So now, so let's say here's our platelet plug, and then what fibrinogen is going to be like, it's going to be this mesh-like network of proteins that are going to wrap around the platelet plug. And then that net of fibrinogen is the clot. Okay, that net is the clot. And then it's going to prevent the clot from dissolving or breaking apart too quickly. And then while the platelets are, again, and then also while this fibrin is squeezing up against this platelet plug, that's going to cause this plug to squeeze out all the fluids from in between here, and then that would, you know, basically you're squeezing out serum. Remember, serum is when you remove all the clotting factors out of blood. Okay. Now, while fibrin is squeezing this platelet plug, it's also going to be squeezing the damaged ends of the vessel together. And remember, I also said that platelets have actin and myosin within them. So fibrin's not only going to be squeezing this plug together, but the platelets themselves are going to be contracting, and then that's going to draw these damaged ends of the vessel, excuse me, in closer to one another as well. All right, which will then, you know, really be a pretty neat factor in controlling bleeding and hemostasis. Okay, so that's how we form a clot. That's how we plug the hole. That's how we stop the bleeding. And then also, while platelets are dumping out this bath of chemicals, they're also going to be dumping out chemicals that are going to promote the healing process. They're going to promote the rebuilding of the walls of the vessel itself. Okay. And then essentially there's going to be an enzyme that's going to be secreted called plasmin that is going to also create the breakdown of this clot so the vessel can completely rebuild. And then, then that essentially is hemostasis, okay, how we control bleeding. The last thing that I want to talk about with this process is some problems that can go along with this. All right, a common problem we see is hemophilia. Hemophilia is a genetic disorder where people are typically missing clotting factor number 10, okay, in that intrinsic pathway. Now, this is a problem because if you're missing any one of these clotting factors, remember your basic biochemistry. When we're talking about these kind of cascade or these waterfall effects from A to B to C to D, to E. All right, if we completely remove one of the parts in this pathway, that pathway is done. Okay, it won't be able to transition to the next point. So if we remove clotting factor number 10, now we're unable to get prothrombin activator going, and then if we can't get prothrombin activator activated, then we can't formulate thrombin well enough, and then we can't form convert fibrinogen into fibrin, and then form clots. Okay, so people who are hemophiliacs then have a hard time forming clots, and then as a result, if they get a cut or get any kind of damage to their tissues to where they're bleeding, they're going to bleed, and they're going to bleed, and they're going to bleed. I mean, it could be to the point where, I mean, you get a routine cut, like I cut myself shaving, or a kid falls off their bike and scrapes their knee, to the point where they may have to go in and get a transfusion. All right, so people that have hemophilia, I mean, they're not going to be playing contact sports in high school. All right, but how bad they're going to bleed is going to depend on how bad the injury is as well. I mean, the shaving example is kind of an extreme example, but you still get the picture. All right. Other clotting disorders. I threw these two words out here because you need to know the difference between them. All right, you need to know the difference between an embolus and a thrombus. A thrombus is a clot. An embolus is a circulating mass. Okay, so a thrombosis or thrombus would be platelets and then fibrin wrapped around them. Platelets plus fibrin. Okay. An embolism or an embolus is a circulating mass. So basically a chunk of something that's not a clot that's floating around. Probably one of the more common types of embolus you're going to encounter in the field is going to be fat. Okay, a fatty embolus. All right. So basically let's say, for example, you break a bone and you're leaking bone marrow into the blood. Or let's probably not, a better example of that would be if you develop plaque in a vessel. All right, so we'll say that's plaque. All right, and as blood is circulating by this plaque, it's going to be rubbing up against, bumping up against this plaque, and that could cause chunks of this plaque to break off. And remember, plaque is just fat, and then as you get older, it's fat mixed with calcium. Then it gets really hard. All right, but if we start busting up chunks of this plaque, they're going to circulate around in the bloodstream, and then they could get stuck in the smaller vessels of the body, and then cause a heart attack or a stroke or other complications depending on where it gets stuck. All right. Now, it's important to know the difference between these two because, for example, if you're in an emergency situation and someone's complaining of chest pains, all right, and you're bringing them into the hospital, you may be ordered or you may be around when they're ordered to be given what's called a clot buster. You can't just look at a person having chest pain and say they're having a heart attack because of a blood clot. All right, they're having a heart attack. All right, now what you're going to do then is basically what a clot buster is when you put these clot dissolving enzymes into the bloodstream that are going to break up some of this fat, and then as a result, hopefully restore some blood flow to that heart tissue, so it can, so we can minimize damage or hopefully prevent damage. Now, if they have a fatty embolus stuck in there instead. All right, remember, enzymes are specific. All right, those clot-busting enzymes aren't really going to do anything to that fatty embolus. Then you just got to get him to the hospital and hope you can get him into surgery quick enough. Okay, so that's something to keep in mind. And thrombosis, you're often going to see used, there's a term DVT, deep vein thrombosis. Okay, it typically happens when you're inactive for a while, when you're kind of sitting around not using your legs, and then basically, sometimes these clotting factors just sit around. Okay, if they sit around, that could that could activate them, and then you start forming clots, and then all of a sudden you start moving around, and then all of a sudden you throw this clot from the deep veins in your legs where the blood was pooling, and then it circulates around. It could circulate in your brain and cause a stroke, or in your heart and cause a heart attack, or somewhere else and cause tissue death. All right. And remember that all an embolus or a thrombosis are going to cause the same thing, an infarction. Okay, and remember, an infarction is when you obstruct a blood vessel and you prevent blood flow from getting through that obstruction, and then that means the tissue on the other side of that obstruction is not getting the blood and oxygen it needs, and it's going to die. It's going to become damaged and it's going to die, and it's going to hurt. Infarctions hurt. There's a reason why people experience pain when they have a heart attack or when they have blood flow cut off in the leg or somewhere like that. The only place in the body where you're not going to feel an infarction is going to be in the brain, ironically. Even though the brain interprets pain, there are no pain receptors on the brain itself. I mean, you ever know anyone that's had a stroke that complained of pain? They don't. All right. So that essentially is, the overall function of platelets and hemostasis. The last topic is going to be blood typing. So covered.